I now expand on the details on single slit diffraction and focus on how diffraction is different from interference. I will outline this by addressing 1. The diffraction intensity pattern. Next, I'll look at the size of the slit opening and the diffraction parameter A over lambda. 3. I'll start talking about the locations of the minimas. And finally 4. The locations of maximas and the secondary maxima intensities. Okay then, I'm going to start off with the diffraction intensity pattern. Suppose light impinges on a single slit. When the light wave is cut off by the slit, different parts of the wave will interfere and cause regions of constructive and destructive in the geometric shadow region. Picture-wise, I imagine that I have this green laser light, and then the slit opening has 2 dimensions. It has the short side, which is A, and it has the long side, which is B. So as the wave comes and impinges on this slit, part of the wave is going to get blocked, and the different parts of the waves then create a diffraction pattern over here. If the region of cutoff is along the long side of B, of the slit opening, the diffraction is more closely spaced. And you can see this in the green right here. So this green is due to diffraction along B. On the other hand, diffracted waves along the short side A form widely spaced patterns. This is shown here in red here. In summary, a beam spreads out vertically after passing through a horizontal slit, while a vertical beam spreads out horizontally. Horizontal beams are vertically spread out. Vertical beams are horizontally spread out. An aperture, which is a single opening, is either rectangular or circular and create different diffraction patterns. A rectangular aperture typically has sort of like this cross-type behavior, whereas a circular aperture gives you circular diffraction patterns. Even though these diffraction patterns appear quite different in nature, their intensity patterns are described by the exact same equations summarized earlier. Let's compare the intensity patterns for single slit and 2 slit. When you look at the single slit versus the double slit, these intensities are all the same. Not true for the single slit. That is, the central maxima for diffraction are much brighter than the secondary maximas. Here's the central. This is the secondaries. Regardless of the size of the slit opening, about 85% of the intensity is in the central max. That means here, about 85% of the intensity falls into here. When you look at all of the secondary maximas, they get about 15% of the light. This is not true for intensity bright fringes. They all have the same intensity. That means this guy, this guy, this guy, they all have equal intensities. The width of the central maxima is inversely proportional to the width of the slit. That is, the width of the central maxima is proportional to 1 over a squared. So if I have a smaller opening, I get a wide central maximum. If I have a larger opening, I get a thinner central maximum. Picture-wise, if I have a small opening, then on the screen you'll see a very broad or wide central max. If I have a large opening, then I'm going to have a very intense bright spot right here in the middle, with the smaller ones being secondary dimmer. If you were to plot the intensity function for different slit openings, this is what you find. I have 4 different slit openings, A4, A3, A2, A1, where they're ranked in this order. So A4, being the biggest opening, is going to have the most intense beam, and it's going to be the most narrow, whereas A1, which is the smallest, will have a very broad central max, and its peak is going to be lower. So what you find here is that if I have a smaller A value, I have one big, broad central max with very likely no secondary maximas. But if I have a wide opening, I get a more intense beam, but then I have numerous secondary intensities. From this image, we could then summarize that a larger slit opening, higher peak intensity, narrow central max, and more secondary peaks. If I have a smaller slit opening, I have a lower peak intensity, wider central max, and there's going to be less secondary peaks. What does the water diffraction pattern look like for a small and large slit opening? Let's look at the applet. So right now here with this water diffraction applet, if you look at the wavelength, it's 5 units. If you look at the slit opening, it's 3 units. So the diffraction pattern is the opening divided by the wavelength. So this is 3/5, which is 0.6. So what you're seeing here is that because the diffraction parameter is small, you don't really see very much diffraction because the wave is essentially being spread out all over the place. Now if I increase this thing, let's say to 9, then 9/5 gives me a larger diffraction pattern, and what you're seeing here is that this is definitely more intense than before, but now you're seeing destructive interference and constructive and destructive. So I'm now, because I have a bigger diffraction parameter, I'm seeing more diffraction. And if I continue to increase, let's say to 15, now my diffraction parameter is 15 divided by 5, which is 3, and you're seeing that I'm getting more diffraction. But if you can compare the intensities, this is brighter than the previous one. And if I maximize the size, this is even brighter now, and I'm seeing more diffraction patterns actually occurring. Looking at the images now from the applet, for this case here, the diffraction parameter A/lambda is 1. And this one, it's 2, 3, 4. And if you look at the secondaries, there's less secondaries for smaller diffraction. There's more secondaries for a bigger diffraction parameter. And what you're seeing here is that this appears dim, whereas if you look at these guys, these secondaries are brighter. And if I just kind of keep going down the line, you can actually compare these two, and what you'll see here is that this has the higher secondary intensities, then they start to step down as I get to a smaller and smaller slit opening. Rectangular and circular apertures. So if I have a single vertical slit of width A, it's going to produce a diffraction pattern that looks something like this. That is, a vertical slit of width A produces a horizontal diffraction pattern. If I now have a rectangular aperture, I still have a slit opening on the vertical part of A, and it still produces that. But now I have to talk about the horizontal slit opening, which then produces this green pattern. So if I focus on the green horizontal slit, a horizontal slit of width B produces a vertical diffraction pattern. Putting this all together, an image of the diffraction pattern for a rectangular aperture looks something like this. And what you're seeing here is that I got a bright maximum in the center because I have both sides that are contributing to the central. And then I get the vertical pattern due to the horizontal slit, and due to the vertical slit, I get the horizontal pattern. Question: from these two images, which aperture is square and which one is rectangular? The fact that the spacings between the minimas on the horizontal diffraction pattern is roughly the same as the minimas on the vertical diffraction pattern, that tells us that the that they have to be the same. So therefore, the aperture is a square. Now if I look at the second pattern, we see that the horizontal diffraction pattern, that their minimas are farther apart. Whereas I look at the vertical diffraction pattern, their minimas are closer together. So if they're farther apart, that means that the vertical slit opening is smaller. Because these guys are closer together, I have a larger horizontal slit opening. Since B is greater than A, then this pattern here is the rectangular aperture. From our discussion of rectangular apertures, let's immediately jump into circular apertures since they operate the same way. Question: can you tell which circular aperture is larger? The one on the left, the one on the right. If I look at this pattern here, note that the minimas appear to be closer together. These appear to be farther apart. There's less of them, there's more of them. Furthermore, the intensity of the central max is brighter on the one on the left, whereas the intensity in this guy is dimmer. From our previous discussion, we see here is that if I have minimas that are closer together and a brighter central fringe, then that opening has to be bigger, whereas if I have a broader central max and the spacings are farther apart, then it's got to be smaller. We conclude then that the one on the left has a larger circular aperture, the one on the right has a smaller circular aperture.